the NPTEL course on storage systems. So, in the previous class, we looked at network file system, and we mentioned that there are some interesting problems with respect to consistency management in NFS. So, we started with NFS2, then went to NFS3, then went to NFS4, and each of them has its own model of consistency, and you can see that has increased to what you can expect from a particular implementation. Now, we would like to go slightly deeper into understanding why is it so difficult to give these consistency guarantees. It's not an easy thing. It's not easy because there are issues like failures in the system that create some complications. We would like to understand this in some depth. That's what we're going to do this class, and hopefully it will give us an appreciation of why is it so difficult to engineer good storage systems. Now, if you look at some of the issues in a large storage system, what are the issues? First of all, you have to have, if it's a very large system, it has to be definitely networked. Without networking, it's not possible to give you large storage system. That means it has to be distributed. And because of failures, if some particular node dies, it may take away its portion of the storage. So, if there is something to be avoided, you may want to replicate the information. So, therefore, one can say without hesitation that large storage systems need to be both distributed and replicated in some form. There has to be some redundancy, it has to be distributed. Now, for multiple reasons, I just give you one reason for it, that was for resilience to failures, but it can be due to also for throughput reasons. It could also be due to disaster recovery. Given the kinds of, let us say, large scale disasters that could be afflicted on storage systems or computing systems, this also is an important issue. For disaster recovery, for example, for banks, there are already regulations which basically say that you need to have at least two sites which are 30 kilometers apart. That means you need to have the information in a bank should be available at least 30 kilometers away. I'm sorry, it should be, yeah, I think it is between 30 and 40 kilometers. It can't be too close. Okay? You can't keep another site about 1 kilometer away. Okay? That's considered reasonable. Okay? So, for variety reasons, you need to distribute and replicate information. And there's also other reasons why you need to do such things. For example, you have security, it turns out to be a holistic problem. That means it is even a small little problem somewhere can actually be magnified into a huge security incident. I think you might have heard about the proverb about a weak link being a problem, right, in a chain. That means that everything is important somehow. Similarly, if you're talking about real time or quality of service, every small thing actually counts. If one part of it is not doing its job well, it can affect the guarantees you can give. So, fundamentally, we can see that you need to solve many coordination problems. So, to me, this is the most important problem you have to solve. There are other issues, but this coordination problem, if you can solve, I think most things we can take care of. And generally, this difficulty arises from asynchronous nature of the systems and failures of characteristics of many real systems. If you look at synchronous systems, that means that somehow you have time synchronization somewhere, and typically time synchronization doesn't work on large scale. It's very difficult. So, if you're talking about synchronous systems, these systems have to be small scale. It cannot really scale beyond a certain size. That means that any large system has to be asynchronous. That means that there is the timing across these systems cannot be mandated through a centralized, let us say, timing device or whatever. It's just not possible. Okay. So, fundamental problem again to repeat is because of asynchronous nature and the failures. Because of this, there are a lot of difficulties in designing a good high quality storage system which can guarantee many properties we look for. I will give you some simple examples of the kind of problems that we can get into. Let us take the case of, we looked at NFS last time. We will look at how NFS can get into some peculiar situations. Okay. So, let us say there can be what is called a directory lockup in NFS. What kind of problem is this? Suppose there is a file which is locked, and this is taking a long time for some reason. We are not going to discuss why it is taking a long time, it is taking a long time. If suppose somebody does a lookup on that file, another independent lookup. Now, it turns out if you do a lookup on that file, the important thing is you are supposed to give some information about that file, which is let us say should be the information you are going to give should be something that is picked up atomically. Okay. That is, while you are looking at it, it can't be changing in a sense. That means the only way we can do it is by ensuring that its parent directory, you take a lock on it to prevent anybody else operating on that file. Okay. So, what will happen is that if you do a lookup on that file which is actually doing some slow operation, some other independent lookup, the directory actually is going to be also, you take a lock on it the directory first before you start thinking of doing something on the file. So, now this lock on the directory is going to be held until the slow operation on that file original operation itself completes. Now, you can imagine a situation where other requests come in which do the same thing on the directory also. So, it turns out that you can come up with a cascade of locks all the way up to root, and everybody is locked up now. Okay. So, this is now hostage to the slow operation that has to finish. Only if that finishes, the whole system actually makes forward progress. While this is going on, the system looks highly unresponsive or dead. We do not know what it is. We do not know whether it is unresponsive, it is just dead. We have no way of finding out. Okay. So, this is not an artificial problem, it happens all the time. Basically, if you take your /user var etc., right, these are system directories. If there is for some reason in one of the directories there is some slow operation, it can travel all the way to root very quick with just 3 or 4 steps, and your whole system looks as though it is dead. Those of you who have used NFS, oftentimes you will find that the system suddenly seems to be dead and then suddenly moves forward, right. It suddenly starts, suddenly seems to be alive again. Okay. It is because of this kind of issues. Okay. But the important thing to notice is that you cannot be sure whether system is dead or it is actually just painfully slow. There is no way to distinguish between this. That is a critical thing that you have to remember. Okay. Of course, if you use some other types of locking mechanisms, there are similar problems. For example, I mentioned that in NFS it uses some additional protocols or services like lock daemons, and if you take those things, we also have a similar problem there. And this can be even worse because lockd is a user process. That means that it has to be scheduled in for it to do any useful thing. Now, let us take a slightly more interesting example, which is sometime recently Facebook had a fairly long outage. Okay. I am just summarizing what I understand from the blog entry that Facebook provided about why their system failed. Okay. I am just trying to give you some idea about the way real systems actually behave and the way they fall apart. Okay. Now, in this system, we will not discuss some of the exact reasons why something exists in the system, but we will just take it for granted that there is some configuration values in a cache. Okay. And basically, this system already has been provided with lots of capabilities of making sure that the configuration values in the cache can get corrupted, and somebody has to check it automatically. Okay. And these cached values come from a persistent store. That means that even if you reboot the system, that value, the persistent store keeps track of it. The cache is basically a volatile value, but it is coming from a persistent store. Now, there could be a problem either in the cache or it can be a problem in the persistent store. Okay. Now, this particular automated system that was designed works well for a transient problem with the cache, but does not really work very well when the persistent store is invalid. For some reason, somebody made an invalid change in the persistent configuration value. It is always possible. Somebody makes a mistake. Okay. Now, if there is invalid change to persistent configuration value, then what will happen? If your system has been written well, the alert client will notice that something in the cached value does not work right. We can detect it by, because for example, things like CRC or a hash or some such thing, we can keep track of whether some configuration value is valid or not. There is some way, some simple way to check. That means each alert client took some cache value, configuration value, and discovered that there was an anomaly. So there is some simple procedure for doing it. Okay, I was mentioning it can be something simple like checksum. Okay. So now, if it finds a invalid value, then it has to go and talk to a database which can give the correct configuration values. Okay. Now, this database is not geared for high transaction throughput, because by definition database tries to be, we will discuss it later, tries to be atomic and consistent, and it provides certain kind of guarantees. So, it turns out databases usually are not able to scale for very large number of requests. Because of this, it turns out that every client which notices this problem, it will try to, because it can't figure out who else is also seeing the same problem. So, everybody makes requests, okay, around the same time. Okay. And because there is a problem with the cache, it turns out that any new queries, okay, they cannot be made to succeed in the cache during and just after the fix. Okay, they do not succeed. So, basically that means that all the new requests also have to go to the database. So, now what we have is a database which has been configured for some reasonable performance, but now all these guys who have detected invalid values, they are going and starting to hit on the database, and any new values which cannot go to the cache anyway, they also start hitting the database, because there is no other way to get the information. Now, this database actually is now saturated. Okay. So, in a sense what is happening is that the queues and the database become very, very long, and oftentimes what also happens is that if some value is not responded within a particular time, these systems can also assume that there is a network problem, they will retransmit again. That means that instead of waiting for some period of time like good citizens, they think that something bad has happened. To make sure that they get their response quickly enough, they go and again requeue their request again one more time. So, in a sense what happens is that in a short time, you can get so many requests to the non-scalable part of your system, that finally what happens is that there is no way to recover from it. So, in this case for example, when this happened in this Facebook situation, they discovered this problem, they tried to see if that was going to resolve itself, it did not resolve, they waited for some time, finally decided there is no way to take care of it, that essentially disconnect the cluster database which was supplying the cached values, which was supplying the configuration values, and then once that was done, essentially the site became unreachable. Similar problems exist in case of Skype also. If you look at, there are incidents of Skype also malfunctioning for multiple hours, and not multiple hours, sometimes even days. Okay. And so, this is not something uncommon, okay, it keeps happening. Luckily, the systems are engineered well enough that this happens, not all the time, it happens once in a while. Okay. So, let us see why failures are so difficult. Okay. The first simpler problem is the following. Okay. This is something called the two generals coordination problem. Okay. Now, in this case, what we have is, there are two generals who are divided by an enemy territory, and the two generals only if they work together they can defeat the enemy. But the problem the two generals have is that they can communicate only through the enemy territory. When you send any messages to the enemy territory, the messages can be seized, it can be corrupted, it can be dropped, etc. So, now we have to solve the problem of coordination across these two generals who can only send messages through the enemy territory. It turns out there is no protocol that can solve the problem, okay, given these conditions. Okay. You can see easily a solution why this should be the case with the following kind of argument. Okay. Suppose you say that there is some way to these two parties, two generals, to agree on when to attack the enemy, because when they attack together they succeed, If they attack singly, they cannot succeed against the enemy. If you say that there is a protocol that solves the problem, then I will say the following. Make sure first you remove all non-essential steps in the protocol. That means finally we are left with only essential steps. So if there is a protocol, first of all I do is take out all the non-essential steps. Because I take out non-essential steps, everything has to be every step is non-essential. But I already said that if I send something through the enemy territory, the protocol step can be seized, duplicated, corrupted, etc. That means I just drop the last one, for example. Okay. That means that the two parties cannot really conclude the protocol. Okay. There is no way for them to conclude it. Okay. So whatever argument you say, I basically will tell you that if they succeed in agreeing it, the last step should be the one that leads to agreement. I just drop that one. Okay. Therefore, there is no way for you to say that they can agree on it. So this is some kind of a simplified or high level argument why no protocol, such a protocol can exist. So in some sense, under these conditions, coordination is impossible. That is first problem. There is another problem which is called FLP result, Fisher-Lynch-Patterson result. It stands for impossibility of distributed consensus with one faulty processor. They show that in a distributed system, if you want everybody to agree to a particular value, if even one of these particular entities can be faulty, then the distributed consensus where all of them agree on a particular value cannot be satisfied. It is not possible to do it. Not just that, you can go with some other results also. Okay. There is a result called impossibility of reliable communication in the face of crashes. Okay. If you have machines which crash, the result is basically shows that there is no way to have reliable communication. What do you mean by reliable communication? Either a message goes or it should go and exactly once. It cannot have duplicates and whatnot. Okay. So this also has been shown to be impossible. Okay. You can even go further down. Some other results have been derived, which basically says that, let us just take the case of data link layer in a network protocol. If you assume that nodes can crash, it is asynchronous, it is memoryless, that is when the nodes, for example, do not remember what they were doing previously. Okay. There is no stable storage by which they can figure out what protocol step they were doing previously. Okay. If you are memoryless and lossy means that I send some packet, it can be dropped. It turns out that there is no reliable data link layer that can exist in this model. Okay. So the foundation that we assume in a ISO stack with a physical layer on top of it a data link layer, it basically says that this is also impossible. Okay. This of course are all let us say extreme kind of results you might say, but once you assume that machines can crash, that they are asynchronous, there is no time synchronization, memoryless, that means the nodes do not remember what they were doing before they crashed, and if you assume that packets can be dropped, then this also is not possible. Actually, it turns out the situation is even more horrifying. Actually, in this paper they show that a system can be driven by sequence of crashes to any global state where each node is in a state reached in some possibly different run, and each link has an arbitrary mixture of packets sent in possibly different runs. Okay. I will suggest you look at this paper to get an idea what all this means, but this is a pretty awful result. Basically what it means is that if I am doing something, if I crash, I might get the packets, when I come up again, I might get the packets, I might send my packets to somebody else, or somebody else's packets can come to me, etc. Okay. All kinds of things like that are possible. Okay. So luckily when we engineer our systems, we make sure that these kind of horrifying things don't happen too often, and that is where a lot of effort is put in, but fundamentally it is a serious problem. Okay. It is not something that we can wish it away, okay, because they come from the basic issues, the ones we assume, for example, that messages can be corrupted or dropped, or the nodes can crash. So following on this, there is another result which is called the Brewer's gap theorem, which tells you the following. that if you are looking for consistency in a system, that is the data that you are that is present in the system is somewhat consistent according to some model, and the data that is there in the system is available for you, okay, availability, okay, I want to be able to use the data, okay. For example, I have a file on a system, I want to be able to access it, availability, okay. And then tolerance to partitions. Basically, if it is a distributed system, I want to have the nice situation where in spite of failures in the system, partition systems, I still am able to do useful work, okay. That is basically tolerance to partitions. Now, this Brewer's cap theorem basically has been shown that, it has basically shown in this cap theorem that not all three can be satisfied at the same time. That is, either can I have two of them, 2 out of 3 at a time. I can either have consistency and availability without this property, or I can have these 2 without this property, or these 2 without this property, okay. So, this cannot be guaranteed, okay. So, all these 3 things are typically important for us, okay. I want my data to be consistent, I want the data to be available, I do not want my data to be not accessible to me just because some partition takes place somewhere else, okay. I do not want a situation where I cannot access something just because some failure is taking place somewhere else, okay. So, all these things are important, but surprisingly or according to this theorem, it is not possible, okay. So, you can see many cases of this. What are the kinds of situations that we come into? For example, I can have consistency and availability only, okay. If you take a single site file system, that is on a single desktop system, I can have consistency with the database, and I can have availability. That is, I do not expect any failures essentially, okay. If there are no failures, I can give you something reasonable, okay. So, all the systems, as long as there are no failures, they work well. If there is a failure, they just block. They block, or they have to get into some uncharted territory of inconsistency or availability, okay. So, all the systems basically work well as long as there are no failures, okay. Or you can go to some situations where you drop the idea of consistency, okay. You say that consistency is that hard, I am willing to accept weaker notions, and then I will try to live with it. You will see that most of web is based on this model. In web, availability is far more important than consistency, because most of the web information is usually not very critical, okay. So, for example, if I am reading a newspaper or whatever, it is not that critical, because news often gets updated all the time. So, if I get slightly inconsistent version of the news, it is sort of tolerable. Same thing with cricket scores. I think it is a common experience that when you are looking at some of these cricket scores, it turns out that after an event has happened, you might get another information which essentially invalidates the previous event that has seemingly happened. For example, my score could be 345 for some 3 wickets, and then I might get another information saying it is 340 for 3 wickets, right, later. It happens because the information usually travels on the web through multiple routes. So, I got the first correct information 345 for 3 through one path, and it somehow became not the preferred route for when the second came, and that actually had the slightly more stale information, okay. So, it turns out both DNS, web caching and disconnected clients, all these things usually do not provide consistency. They give you availability, some information available, some score is available to you, okay, but no guarantees on how good the score is, okay. Same thing with DNS also, okay, because it also does some kind of caching, and if the information is incorrectly updated for a small window of time, it can be given to you, okay. And basically, in all these cases, essentially you are optimistic, okay. So, you are basically saying that it is okay to have slight inconsistent values, it will be corrected soon, sometime soon, okay. This is optimistic version, okay. So, because of this, sometimes you will see that there is a need for conflict resolution. That means I got 2 scores, I mentally at least have to resolve what happened, okay. And in the case of cricket scores, you might not do any conflict resolution, but in some other cases you need to think about what could have happened, why this is the case. And for example, email might have come one way and some other email might not have come some other way, and I might have to understand what really happened and based on that reason something about it. Okay. And typically here you have the notion of leases, basically because it is difficult to be strict about consistency. So what I can say is, as long as I give you some exclusive access to something for a period of time, and this is governed by time, as long as my time synchronization is very good, then I am reasonably safe. But time synchronization itself is not possible to be very accurate, because there is some, it's got a, you cannot do time synchronization to better than few tens or hundreds of millisecond accuracy. It's not possible. Therefore, that means that there is still a problem, and that basically means that I am assuming that even if I take a lease, there could be some corner cases where two parties think that they can go ahead and update this thing at the same time. Okay, that's possible. Okay. So you can also have the situation where there is consistency and what is it, tolerance to partitions, but you don't have availability. Okay, and this is a typical situation. You have distributed file system and database and distributed locking, and basically here what happens is that if you find that some network partition has taken place, you basically stop giving access to certain data. Okay, because you are concerned that people can get wrong data, you basically take the extreme step of saying, I don't have any data for you for the time being. Okay, till things are reasonably clear. So if you use what is called majority protocols, what is this? Basically, if there is a partition in the system, what you do is you have something called majority protocol. Basically, you vote. If majority people agree on a particular value, you basically say that that is a value. So in a sense, you are able to tolerate partitions, but now the minority partitions, they may not be available. Okay. So that's why there is no availability. Okay. So some part of it can be proceeding, and there is tolerant to partitions because some parties are still able to get some work done. Okay. And but certain things are not available. Okay. So here typically turns out that pessimistic locking is done. That means you take as extreme steps as possible to ensure that consistency is let us say guaranteed. Okay. So we will see that databases usually work in this area. Okay. And I made a mistake, sorry. Here is where web usually works in this area, databases work in this area, file systems work in this part, partly sometimes, partly here and partly sometimes here. Okay. We will come to that details later. Okay. Yeah, sorry, I will do it right now. Okay. So let us just look at high level, what is the difference between file systems and databases, okay, at high level. Okay. What is a file system? It is a persistence and naming service for all applications. The critical aspect about this is that there is no information application, and what information is critical, that is not given to you. Okay. All that the system can do is differentiate between two types of information, data and metadata. Okay. That is the only thing that the system has got access to. So what can a file system do? Because it has got only two types of information, two ways of classifying things, data and metadata. It can guarantee possibly consistency of metadata, that is one possibility. Anyway, this is needed because metadata is kept by the file system to manage the data. So this is something which is file systems. Okay. So it is needed anyway for file system sanity. It can't abandon consistency of metadata. Okay. So it is something it is critical. Okay. The only issue is that in spite of worrying about consistent metadata, even then it can get corrupted. Okay. If it gets corrupted, the file system says, I have no real serious information about what to do next best. Okay. I will fix it in some suitable way so that system can function again. I want to make the system available. That is my perspective. Okay. And that is what is, some of you might have used something called FSCK older systems, and even if you have what is called generating file systems, once in a while you have to do FSCK. Okay. It is still necessary. Okay. You can avoid it to some extent, but memory corruptions, all those things, when they come in, you can't really avoid it. Okay. So consistent metadata is taken seriously in the file system, but data consistency may not be considered very seriously. Okay. Because the file system has no idea, because nobody has told it how important certain pieces of data are. Okay. So, the file system optimization is basically the following. I do not want to be very slow, okay, because if I am very slow, then nobody will use my file system, and all the basically this is the most basic service for persistence in the system. If this is slow, then the whole system really it becomes atrociously slow. Okay. Hence, the idea here in file system is to sort of weaken the data consistency model and make the system reasonably responsive. That is the basic idea. And why is this an important issue? Because you are dealing with things like disks, which are amazingly slow compared to memory. Okay. They are order of about 5 orders of magnitude slower than memory. So, because of this reason, the file systems usually take some the bargain they have entered into is the following. Okay. That since you want some reasonably responsive system, I will relax the consistency condition for data. I will try to be as far as possible consistent with respect to my data, because that is needed for my own sanity. Okay. So, how does this file system do it? It uses synchronous operations in case you need to have data consistency. Now, what exactly do I mean by this? Basically, in file systems, you can, if some operation has to be done, it has to finally make its way to the disk so that it becomes persistent. Now, I can ensure that I do everything synchronously. Every time something changes, I immediately flush it to disk. That is one possibility. The second possibility is, if I change something, I do not flush it to disk immediately. All I do is I queue the flushing, but I do other things afterward. That is another possibility. The third thing is I do not even queue it. It is what is called delayed writes. Okay. There are 3 possibilities. One is I do it and wait for the flushing to have happened on the disk, then only I proceed. That is the most conservative or the synchronous type of operation. Okay. The second one is I am doing it asynchronous write. What I mean by that is I queue the write, I do not know how long it is going to take, so I do not want to keep waiting, so I just go and do other things. Okay. That is asynchronous operation. The third one is delayed write. I do not even go and queue it. I will expect that some time later somebody, because of some urgent reason, is going to do it for me. I am not going to do it myself. I am not even going to queue it. I am not going to wait for it. I am not going to queue it. Okay. Now, because of this, it can turn out that if you use, for example, the delayed write, whoever is going to flush it to disk has no idea about the dependencies of each piece of data with respect to others. So, something which is important to be, there might be a particular order in which you have to flush the data. For example, if you look at the cricket scores, what you wanted was that 360 runs after 3 wickets should come first, followed by 360, followed by 365, whatever, right? You want a particular order it has to come, right? Similarly, data also can have certain orderings, but because in delayed writes, somebody else other than you is flushing it to disk, they might not know the ordering between these things, and they will flush in probably in incorrect orders. And if there is a crash of the system, you might see inconsistent ways of the data that has been flushed to disk. Okay. So, this is one problem the file system has got, as long as you are trying to make your system responsive. So, there is a, in a sense, you have to understand what the file system is trying to do for you. Okay. It can't give you the guarantees that you seek for, except at the cost of being extremely slow. So, that is why it is not a default. On the other hand, a database uses something called asset semantics. Okay. Actually, a file system also can use asset semantics. Okay. It's just that it becomes too slow for it to be useful. Okay. A database, on the other hand, usually deals with some real world important information like bank balances and other things. It can't take this approach, because if your bank balance becomes inconsistent, it is going to be a serious issue. Therefore, databases, in spite of slowness, they will insist on a particular set of semantics. This is the asset semantics. Okay. That is the reason why databases cannot scale to the way a file system can scale. So, the number of operations, that number of transactions an database can do typically is at least 1 or 2 orders of magnitude slower than the kind of operations that a file system can do. Okay. So, what are the kinds of things that a database is, let us say, trying to guarantee? One is atomicity. What is atomicity? It turns out that you want to ensure that either some transaction happens or not happens. Okay. You cannot have some in between situation. Okay. Either your bank transaction happened or not happened. Okay. A consistency of data. If you have multiple transactions, there might have to be consistency across these transactions. That is, for example, if I withdraw some amount, I write a check from my account to somebody else's account, it should decrease from mine and increase in the other person's account, but the amount of decrease should be equal to the amount of increase in the account. That's a consistency condition. Again, this is an application idea about consistency. It is not inherently known, for example, to anybody else other than application. Okay, that's a consistent data. So database also has to be responsible for this. And isolation from other transactions. That means one transaction should not interfere with other transactions. Even if I concurrently run it, it should not be the case that one transaction somehow negatively impacts other transaction. Okay? Each transaction should seemingly, in spite of being done concurrently, should seemingly be just as if it was done as in isolation. Finally, durability. I do a transaction, any effects that I should see, okay, should be persistent. Okay, that's durability. Now, this one part which the database depends on storage system. Okay, rest of it is again actually it has to handle it itself. Okay, now if the database is running on a file system, then the file system database depends on the file system to provide the durability, and the file system in turn has to find some mechanisms by which whatever things have happened with respect to database that has to be made persistent has to be made durable, so that if the machine dies and comes up again, whatever changes have taken place actually can also be seen again. Okay. So this turns out to be the responsibility of the storage system, and the database can directly do it itself, or it can go through the file system. So if it goes through the file system, then it has to make sure that the file system understands the importance of whatever it is changing. So it has to indicate through some mechanism. Usually this is done not by through what is called mount options. A file system can be configured saying that all these operations have to go synchronously or in some particular fashion which ensures that things become durable in some particular way. So there has to be some understanding between database and file system, or the database can directly talk to the storage system, and the database can tell the storage system specifically, please do this synchronously. Okay. I'm going to wait till you are done. Okay. So that also is possible. Okay. It turns out the durability is not a trivial thing. I will come to that soon. Okay. So let's some brief remarks. Basically, it turns out if you look at operating systems or networking, etc., typically they are good at availability, not so good at consistency. We already looked at NFS as a good example of this, right? So basically in NFS what we are doing is to avoid too many round trips, clients keeping on checking whether some data is valid or not. Okay. Sometimes they do cache the attributes, therefore they can there is a window during which they assume that data is not been modified by somebody else when it has been modified. Okay. Similarly, you can have in a cluster, it is possible to have consistency and availability, but generally it is very hard, and basically again because of reasons for failure, etc. Okay. If you have distributed file systems or databases, they are better at consistency, but they are not good at availability. Same is the case with wide area databases or disconnected clients. Okay. There are some problems here also. Okay. So basically you have to decide what kind of model you want and make sure that the system is engineered for that particular reason. Let me briefly mention durability, why it is so hard. Okay. First of all, if I am talking about a large storage system which is going to guarantee durability, it itself is composed of many parts. Okay. Now there is a recursive problem you can see now. Okay. Because if there is a large storage system, it has a lot of data itself. Now how does it keep its own data or metadata consistent or atomic with respect to changes? Okay. For example, what are the kind of changes that can be there? It is possible that one node dies. Somebody has to keep track of that this particular node or disk has failed. This has to be made persistent, because there is some kind of a table somewhere saying that this particular disk died, right? And other people could be referring to it. So it has its own metadata. Now how is this also guaranteed? Okay. So it's a recursive problem here. Okay. Okay. So So, in a sense, if you look at ACID property, the first 3 parts the database tries to achieve, but the durability itself is recursive. It actually can be, a lot of people say in the storage systems area that to give you that quote ACID property for the storage system, they might again use ACID, but again the D part of that ACID which storage system itself does has to again be guaranteed through some other mechanism. Okay. So, there is a fairly tricky issue here itself, and so these are basically done by some careful engineering to ensure that the problem becomes smaller and smaller, so that finally you can say with some high probability I guarantee that something is persistent, therefore the whole chain can be made to stand on that particular assumption. So, basically all I am trying to say is that it is true that there are many impossibility results, right. For example, we looked at all these cases, right, all these issues. So, but that does not mean that you cannot do certain things. I will give you an example about a protocol like the TCP protocol. We know the web is very widely used because we use TCP protocol, and TCP protocol really works quite well. Okay. But we notice that there is a result which basically shows impossibility of implementing reliable communication in case of crashes. So, it turns out if you think carefully about TCP, it has been possible that TCP really works for us because of very well carefully done engineering. Okay. Let me give you an example of the kinds of engineering that has to be done. Okay. Suppose, what is the TCP connection identified as? It is identified as IP address and port number on the source side, and IP address and port number on the destination side. Okay. Now, if you think about this, this is a finite sized piece of information. Now, that means it is a finite system. In a finite system, you can always repeat. In an infinite system, it is difficult to say that you can keep repeating. Okay. But in a finite system, for example, if the number of possibilities is 2 to the power of 16, it is always possible for me to, if I keep reusing port numbers, etc., I can possibly repeat that thing, right. So, because it is a finite size, if I start a new connection and by sheer bad luck I have the same signature as this one, that is, it has the same IP address, port number of source and destination, okay, then it is possible that some packet of the previous connection which was hiding somewhere in the internet somewhere suddenly comes and drops into my current situation, then I might have what is called a packet insertion problem. Why is this not unlikely? Because you notice that if I am talking to 2 machines, only 2 machines, okay, the IP address on the source and the IP address on the destination both are same anyway, it is not going to change. If I am talking to the same server on the destination side, the server port number also is the same. The only thing that is going to be changing is the port number on the source side, right. Now, if I use my port number, I cycle through port numbers very fast, okay, then I can essentially repeat the same identifier for the connection. So, because of this, there are various methods in TCP protocol. If you look at the RFC, it tells you what all to do to make sure that this kind of packet insertion is as unlikely as possible. Okay. I do not have time to go through all the details exactly how they do it, but there are many methods by which they do it. They have something called sequence numbers, you might have heard about, which are used. It has got something called 3-way handshake, which also used to precisely avoid this particular problem. Again, the details about why it is 3-way handshake, not 2-way handshake, it is because of precisely this reason. Okay. And in spite of all the methods they have used to avoid this problem, just as a fallback in case all these methods fail, they have one more requirement. If you look at this section 3.3, they tell you that a node cannot reboot faster than within 2 minutes after it has crashed. Okay. That is, if a machine crashes, it should not reboot within, it has to reboot at least only after 2 minutes. Okay. Some such rule is there. Okay. Or you have to ensure that it remembers the last sequence number before crash. That means that anytime you have any sequence numbers, you have to put it on stable storage. Okay. It means that it has to be anytime you change any sequence number, because you send a packet to change the sequence number, it has to be available in stable storage, then only you can send the packet. Now, you know that sending packet is going to be much faster than saving it to stable storage, because stable storage nowadays means typically only disk. So, either you do the hard thing of remembering last sequence number, which is very, very slow. Essentially, you cannot send packets faster than disk operations. Okay. Either that, or you have this rule and various other rules, and typically this rule is one which is not very well known. You cannot reboot a system faster than 2 minutes, okay, precisely to avoid this kind of issues. Okay. So, it's a lot of engineering that has gone in to make sure that you still survive all these impossibility results. Okay. So, that is the reason why TCP is still surviving. If it was not done well, there was no chance it would work on the scale on web as it is happening. Okay. So, our idea is that even if you have some problems with various impossible results, it is possible for you to do something reasonable. Okay. So, there are various ways to get around some of these problems. I will just go through a few of them right now. Okay. One obvious way to say is, why don't we avoid failures in the first place? Okay. Now, this is not a trivial thing to do, because we are talking about real systems, and real systems are many types of ways in which can fail. Disk can fail, batteries can fail, the CPUs can fail, they can get overheated, all kinds of things like that. Okay. So, this thing is almost impossible. The only other thing you can do is to reduce the chance of failure, and usually if you try to reduce the chance of failure, you are talking about extremely expensive systems. Okay. So, and these two types of operations are also, types of approaches are also followed. I think some of you might know that if you look at Google file system, they decided that instead of trying to reduce the failures, they went for trying to manage the failures. Okay. Whereas, if you talk about what is called enterprise systems, they try to reduce the chances of failure itself. Okay. So, by having redundancy and other kinds of things. Okay. So, that design becomes typically expensive, whereas if you are able to manage failures, typically if you do it well, you can reduce the cost. Okay. So, this approach of avoiding failures is typically extremely costly. Okay. Other possibility is make sure partitions are repaired within latency requirements for a request. That is, something fails, you somehow make sure that the partitions get repaired before the next request comes in. This also is a hopeless task typically. Okay. So, or you try to go to slightly more relaxed situations. One example of a approach is what is called time asynchronous models. You basically assume that a real system has unstable periods followed by sufficiently long stable periods. Okay. And there is this particular aspect has been worked out in some detail, and this is something called failure aware design, and unfortunately this has not been seriously taken up, because there are some interesting projects that were attempted with this particular model, but somehow it could not be made to work, because this particular design, failure aware design, is fairly complex. Okay. This also has failed in some sense. To me, it looks like a very promising approach, somehow it has not taken off. Okay. Other thing to do is, do not do anything when partitions are present. Okay. Our big problem is that even if this looks nice on the surface, it is impossible to even detect failure, okay, when failure has taken place, because as I mentioned earlier, sometimes the systems can be arbitrarily slow. You do not know whether it is actually failure or is it slow. Okay. And I gave you that Facebook example where the queues can build up to such an extent that system is unresponsive, and even after 2.5 hours nothing is going on. Okay. All your requests are just sitting there. Okay. Somebody finally has to disconnect the whole system and drain out all the requests, and then once everything is, all the queues are cleaned out, then you can send again. Okay. So, this also is sort of not a feasible thing. The other issues, other ways to handle it also. For example, one researcher has suggested that the reason why these things are happening is because of some root causes. Why don't you attack the root cause itself? Let us try to understand an example of a root cause. Okay. Once, as data center networks become bigger and bigger, it turns out that the software stack increasingly becomes one-to-many communication patterns, okay, multicast. Take Facebook or Twitter, all those things, right. Basically, you are talking about one piece of information that has to be sent to multiple parties at the same time. Okay. Multicast becomes very common, and it is also the case because if I update something in a replicated system, update in one place, it has to be replicated. The update has to be replicated to multiple places. Okay. So this multicast is a very natural phenomenon. If you are trying to, either because of the way the new communication patterns are showing up, Facebook or Twitter, or because of availability other reasons. Okay. Multicast is a very common requirement. Okay. So essentially, there is something called publish subscribe models. They push data to many receivers simultaneously. And also, as I mentioned earlier, they allow clustered application servers to replicate state updates and maintain coherent caches. So this the fact that you need multicast is I think fairly clear now. But the issue is that if you want to do this particular kinds of multicast, right, it turns out while it's necessary, it has certain problems. Okay. For example, it doesn't have flow control. That means that it can essentially push the system into very unstable situations. Okay. So IP multicast doesn't have flow control. Okay. You can try to understand why that's the case, but the ones you have flow control across such a multicast, it's very difficult because you have to manage multiple nodes, all those things. It's just totally hopeless. Okay. That's the reason there's no flow control in this. Okay. Similarly, you can have issues about security, etc. Okay. So basically, for this reason, big users like Amazon, for example, they tell you that you cannot use multicast in applications. They tell you mandate it's not possible. Okay. So on the one hand, it's very critical, but it's impossible to provide that kind of support. It turns out to be, if it is provided, it will break the system someday. Okay. So you are in a very peculiar situations where it is necessary, but you cannot use it. Okay. So, and it turns out the reason why this flow control problem comes in, some people have suggested, is because the IP multicast addresses are scarce. Because you have small numbers of this IP multicast addresses, therefore, it turns out that if they get used up, the hardware limits of these multicast addresses get used up, you finally have to depend on some other facilities manufactured by the kernel, for example, and because it is now not done in the hardware, it is done in the kernel, it turns out the system again can get overburdened. So one of the things that people have suggested is that there are some problems, why not increase your resources of, for example, multicast addresses sufficiently so that you are always away from it. It's costly, but that's one way to handle it. Okay. There's a lot of cost to it, but if you do a good job, many of the problems that we talked about disappear. Okay. So this is one way to do it, throw money at it, but this is not widely used. Okay. I will stop with one other example of the kind of problems that we often face in large scale systems. Of course, storage systems also fall into this category. Sometimes you have, if you are using multicast, they also have what is called oscillatory behavior. What exactly is oscillatory behavior? See, nodes, you are talking about a large scale system, there are many nodes, each node is doing something. For example, it could be responding to some requests from a web, and therefore it might be doing Java execution. Java has something called garbage collection. While garbage collection is going on, usually it pauses, it can't do other things. Okay. That means the node actually is, for the time being, not responding to certain things. Okay. Similarly, Linux scheduling delays could be there, or somebody is flushing data to disk. All these things can create certain disturbances in the system. That means that while that node is disturbed, it may prevent the node from forwarding packets, okay, because the application thread does not respond, okay, etc. Okay. So what is the issue here? Because the node is not forwarding packets to downstream, but upstream something is still coming in. Okay. So, the root is still continuing to send it. So, I am still getting the packets. So, finally, what happens is that if it is engineered well, I am going to send a response back saying, I am not able to send out something, but I am still getting too much stuff from my upstream guys. So, I will tell the upstream guy, please stop sending it. Okay. So, because of this, the previous guy, the upstream guy also faces the same situation. Now, he is not able to send out things, but he is getting stuff from his parent also. So, finally, the whole of this network, the disturbance at one level travels all the way to the top. Okay. So, essentially all the buffers on path from the root to the node become full, and the root sending throughput drops to very low values or 0 now. Okay. So, again, once this particular thing, that disturbance passes away, again they will slowly come back towards normal situation. It takes time. So, it goes on oscillating between reasonable throughput and very low throughput, keeps happening all the time. Okay. And actually people have shown that if you have a very large tree, let us say 10,000 to 60,000 nodes, and this is actually a small system in current days web. Okay. I think Google has, for example, at least 1 or 2 orders of magnitude more number of nodes. Okay. In a very large tree, they have shown that when each node is disturbed only for 1 second in an hour. Okay. You have so many nodes, each node is disturbed only exactly 1 second in 1 hour, that is 1 in 3600. Okay. The throughput degradation can be as much as 90%, even the message loss is negligible. Okay. So, it is a dramatic drop even for something like 1 in 3600 kind of disturbance for each node. Okay. So, that means that your behavior of the system is somewhat problematic. You can't really say when some system is working, when it is overloaded, when it is dead. You really can't say any of these things. Because of this, it turns out that anybody who is using timeouts in the system, they might suddenly discover that system is unresponsive. Because it is unresponsive, you think it is dead, or you basically say that I will retry it, thinking that hopefully my packet has been lost somewhere. I will retry it and see if it goes through the second time. So, I might actually add more work to the system, and that actually keeps building it up, and that might actually drive the system to some really bad situation. So, there are various reasons why you can't really say what is going to happen in the system, and so your ability to guarantee availability or resistance to partitioning, etc., becomes that much weaker. Okay. We will continue from here in the next class.